Solution to question number 7 for dynamical systems and chaos. 7a is concerned with a pendulum equation, and we want to show that the origin is asymptotically stable in the region mod x is less than pi. And for part B, we have a Aikida mapping, and we want to show that this expression is true, where ES is the steady state. Okay, so for question 7a, we're using a Lyapunov function given by this expression here. So dv by dt is partial dv dx dx dt plus partial dv dy dy dt. So here is partial dv dx, just straightforward partial differentiation. dx by dt is y, and here's partial dv by dy, and the expression for dy by dt is here, so we just substitute that there. So now we have to expand this bracket out and simplify, and simple algebra gives you this expression here. Now we want to know whether this is positive or negative, but the clues given in the question, we do want to know, we want to prove that the origin is asymptotically stable, so we know that this expression here has to be negative, which means that x times sine x plus y squared has got to be positive inside this bracket. And if you plot x times sine x using easy plot in MATLAB, then you will see that x times sine x is always strictly positive when mod x is less than pi. So you can check that with MATLAB. And because x times sine x is always positive in this region, then dv by dt is negative, and the origin is asymptotically stable, where a and b, remember, are both positive. For part B, we have the Aikida map. If we rearrange this, we get this expression here. If we take the modulus and square, then mod en squared is equal to this expression, and then therefore en is equal to this, and this is our inverse mapping. So en plus 1 is a function of en, that's our forward mapping, and then en, this is a function of en plus 1, that's the reverse mapping, so this is the inverse mapping. For the second part of the equation, we want to show this is true. Remember, we were given that the modulus of a squared is a times its conjugate. So if we rearrange this equation using Euler's expansion, so here is a, after rearranging this equation using Euler's expansion, so this is a, so we can easily find the conjugate of a. So we multiply a times the conjugate of a, multiply out the brackets, and we get this expression. And then we simply differentiate this d mod a squared with respect to d mod es squared, and simple differentiation gives you the result here. So that concludes the answers for question number 7.